let's go on to the alternating series test. Now, if you notice, if you go back and look at all of the tests that we've done so far, it says that if AN is a series with positive terms, okay, then use this test, right? Use the limit comparison, direct comparison, whatever. Integral test. They all have to have positive terms. What about series that don't have all positive terms? What about series that have some negative terms? Well, that's where this alternating series test comes in. What is an alternating series? An alternating series is a series that, I mean, the name kind of gives it away. Every term alternates between being positive and negative, okay? And it has to be every single term. Like that means like the first term is positive, all the odd terms are going to be positive. The second term is negative, all the even terms have to be negative. And if any of them deviate from that at all, then it's not going to be considered an alternating series. In other words, you can't have like two negative terms, then three positive terms, and then skipping back and forth like that. It has to be every single term alternate between positive and negative. So if you have a series like that, an alternating series, then you can use this alternating series test. Okay, so just notice the form of an alternating series. Any series that has this form, where you've got a -1 to the n, or a -1 to the n plus 1, or a -1 to the n minus 1. Those are really the three that you'll see. Any series that looks like this is an alternating series. So this term right here is the giveaway. Once you see that thing in any series, or the n being an n plus 1, or the n being an n minus 1, that is an alternating series, okay? Provided, of course, that that bn has to be positive by itself. In fact, you can see that on the worksheet. It says bn has to be positive for this to work. Because if this one had, in fact, it says strictly positive still. Because if this one had any negative terms, well, then that would cancel the negatives, some of the negatives there, right? And then it couldn't be considered alternating. So the bn itself has to be positive. All right, so now what's the alternating series test? This is another really simple test. In fact, this test is one of the most simple there is, fortunately, because we like easy tests and this kind of thing. It's just a two-part test, and you can see both parts there. You have to have bn be less than, bn plus 1 be less than bn. And you also have to have the limit of the terms of the series, the non-negative terms, has to be 0. Notice, be really careful about this. That bn there is the same as this bn here, okay? So notice what is not part of this part of the test. That is not there. You see, the -1 to the n is not there. All you're checking is just the terms that don't have that -1 to the n on it, okay? Be really careful about that. And I'm telling you this because I see on the tests, in previous semesters anyway, that people will attempt to include that -1 to the n in the limit. It should not be there. The only thing that needs to be there is the non-negative part of it. So let's see how this works. Alternating series test. Again, it's really simple. Once you get the hang of this test, it's pretty nice, pretty easy to check. So here's our series. I'm just checking, does this thing converge or not? That's the question, right? Okay, so clearly this is an alternating series. It's got that -1 to the n. And just to be clear, you could write this thing like this. You could write it like this. Right, and so if you do that, this is pretty clearly identifying that that is the bn term right there. So that when we do this part of the test, that is the term that we're going to be checking. This has nothing to do with this part of the test, okay? Again, just try to keep that straight. So what does the alternating series test tell us to do? It says we have to check two things. What's the first thing? One, check that bn plus 1 is less than bn. And again, this only compares just that. And the -1 doesn't do anything. This has nothing to do with either part of this test. All this is doing right here, all that's doing is identifying that this is an alternating series. Every part of the test, or the two parts of the test that we actually do, have nothing to do with the -1 to the n. So what's the first part? bn plus 1 is less than bn. Well, what's bn plus 1? It's just what you get when you replace n with n plus 1. So do that. Replace n with n plus 1. And then don't do that. Just do that. So this is the bn term right here. Sorry, the bn plus 1 term here. And this is the bn term right here. So I'm just checking, how do they compare? Well, again, if you add anything to the denominator of a fraction, what effect does that have? It has the effect of making the fraction less, right? And so we can pretty obviously just point that immediately to the left. And so that's check. That is true. That is the first part of the alternating series test. Obviously true. We don't even have to do anything, just except say that it's true. The second part of the alternating series test says take the limit as n goes to infinity for the terms of the series that we're interested in. That's the 1 over ln n. And again, this is pretty obvious that that limit is 0, right? I mean, if I plug in bigger and bigger numbers, ln n in the denominator, it's going to get to head towards 0, right? And so that part of the test also passes. Very easy to check. So it's passed both parts of the alternating series test. And so together that tells us the series converges by the alternating series test. This next part, the alternating series estimation theorem, this is another way to estimate the sum of a series. You can see the alternating series estimation theorem. It says S is equal to this. And what they're doing there is they're just saying, let's let S be the sum of this series, or whatever it happens to be. And it satisfies both parts of the alternating series test, meaning that it's going to converge. Then it says that this Rn, what's Rn? That's just the remainder. The remainder being the difference between the actual sum of the series and the nth partial sum of the series. Okay, so S itself represents the actual sum of the series, right? So whatever the actual sum of this alternating series happens to be. Sn then, again, remember, just represents the nth partial sum. So instead of going to infinity, right, maybe I stop at some number up there, right? Like the 10 or 15 or 100 or whatever, right? So everybody clear on that? This would be an approximation to the sum. This would be the exact sum. And if you take the exact sum minus the approximation, well, ideally, you would want that to be as little as possible, right? Because if you're trying to approximate it, you want to be as close to the exact sum as possible, or at least as you want to be, right? And so that difference is called Rn. That's the remainder. Well, again, we want that to be really tiny, especially if we're trying to approximate it. And so this theorem, this estimation theorem, will tell us exactly how close these two are to each other. In other words, how small that error actually is. And you can kind of see right there. It's simply as small as the nth term of the series. That's it. So for example, suppose I had this as a series, and I know that that's going to pass the alternating series test, okay? So what that thing is saying is that suppose I want to figure out how small that error is. Well, if I look at let's say the 10th partial sum, okay, the 10th partial sum, what's that going to be? That's like if I count up from n equal 1 to 10 of -1 to the n over n there. And so you can kind of see that that would be like, let's see, -1 plus 1/2 minus 1/3, etc., right? Plus 1/4. And then I would stop up here once I reach 1 over 10, okay? It turns out that the error is going to be less than what? The n plus 1th term there, right? And so what is B11 in this case? B11 is 1 over 11, right? And so what that's telling us is that if I add up these first 10 terms here, I'm going to get some number, right? How close is that number going to be to the actual sum of the series? Well, according to this theorem, it's going to be within 1/11th of the actual sum of the series. Okay, so that means that whatever sum that actually is, I'm going to have be plus or minus 1/11th away from the actual sum. If that makes sense. Okay, so this estimation theorem just tells me if I want to get an approximation that's good enough to however many decimal places, I can figure out where I need to stop by looking at this term that comes right after it. You see what I mean? So like on that example 2 there, if I want this to be correct to 4 decimal places, I would want this number to be, whatever that Bn is, I would want that to be less than 0.0001, I guess, on the example 2. And so I would just say, okay, well, what's going to make that happen? And I plug in until I reach some number and say, well, what term do I need to go out to in order for this number here, Bn, to be less than 0.0001? Okay, so this is just another estimation thing. If I want to estimate the sum of a series, I have a pretty good idea, or I have an exact idea of how close I will be to the actual sum of the series. If I go out to the nth term, I just go one more term beyond that, whatever that number is, the error is going to be smaller than that. Okay, but like I said, that's just something that's there. It's, again, just to approximate it, just to give us an idea of how close we'll be to the actual sum. All right, so we got two problems here. Yeah, I'm just going to share this with you. So he's just checking the parts of the alternating series test. How come you're doing that derivative there, though, Michael?
I was doing it just to show that it's decreasing.
So that's another way to show that bn plus 1 is less than bn, I guess. Is that right?
Yeah.
Yeah, okay. So you can do that directly also, just show that the bn plus 1 term is less than the bn term. Or you can do what Michael did here and just show that if you take the derivative and you find that that derivative is negative all the time, or at least negative for numbers that are bigger than that, then that's good enough too. Because if it's decreasing, then that means that the n plus 1 term is definitely less than the n term. So there's really two ways to do that, the way I showed you and the way that he's doing here by the derivative. So on part 2, it fails one of the steps of the alternating series test. You see that right here? This is diverging because this limit, although 2 to the 0 is 1 though, right, Michael?
Oops, sorry. Yeah. Yeah, it is.
But still, right? It's not 0, that's the point. It should be 1. But the point is that it is not 0, right? And since it's not 0, that means that this diverges. Okay, so and that's another thing just to take away from this. If you have a series that fails the alternating series test, it is going to diverge. Okay, so if it fails either part, it's going to diverge. So that one does fail, part 2 of the alternating series test, so divergent.